Today we're going to be doing a depolymerization reaction exclusively on PET. Now you can see the structure of the monomer here, where the polymer makes up n number of linked monomers. Our method today is going to be using basic conditions and heat to cleave the ester bond and make it to the corresponding acid. You could use an esterase enzyme, but I'll leave that for the biochem lab. Alright, so I didn't show it, but I set up the reflux condenser and now we're heating our mixture. So with the sand bath, you want it to be exactly at the solvent level. The sand allows better dissipation of heat, and the boiling point of the alcohol is higher than water, so we can't use a water bath. Okay, so I'm going to get this up to temperature and come back when it's starting to reflux. I've covered the apparatus in aluminum foil to kind of contain some of the heat and allow the apparatus to get up to temperature more quickly. As you can see, I made a little hole so I can still see whether or not my solution is refluxing. So once it starts refluxing, I will start a timer for an hour, and then we'll do our workup. After 30 minutes of reflux, let's take a look. So you can see a lot of white suspension of a solid, but it looks like our reflux is going, so I'm just going to cover it back up and wait another 30 minutes. Alright, so let's go over the workup for this reaction. My reaction is refluxing right now, so after that's done, we're going to let it cool to room temperature. Then we're going to do our first 10 ml water wash. There will probably be still some insoluble substances, so after that we're going to filter. The purpose of this first wash is to extract our product salt, which is shown right here. Okay, so once we get the insolubles out, we're going to add it to a SEP funnel. We'll drain the aqueous layer. We're going to do another 10 ml water wash, and then we'll combine the aqueous layer. Now we're going to slowly acidify the solution, making sure that we don't do it too quickly. And then we're going to add ice. What this will do is protonate the acid and make it water insoluble. After we have the product, we're going to take an HNMR. Let's take a look at our product and try to predict what the NMR may look like. Okay, so the first question I ask is, how many equivalent hydrogen groups are there? The first step, if you want to be extra careful, you can always just draw in every single hydrogen. Boom. Okay. So let's look at the OH peaks. This one and this one. Okay. Do we think they're equivalent? Typically they wouldn't be equivalent, but because this is para-substituted and the molecule is highly symmetrical, these should show up as one peak together. That be it, the peak should be pretty broad, and it might not even show up because of deuterium exchange with the solvent. Okay, and because of that symmetry, all of these hydrogens are one group. Okay, and so if I drew them out over here and labeled them HA and HB respectively, and we would expect HA to be a broad singlet greater than 10 ppm, probably around 12, with an integration of 2 hydrogens. HB should be somewhere in like the 7 to 8 ppm range. It should also be a singlet and with 4 hydrogens. For anybody on YouTube who may have taken a higher level spectroscopy class, please just note that this is for undergraduate organic chemistry lab. Okay, an hour has passed. We're going to stop the reflux and let it cool down to room temperature. Touch your sand bath because it's going to be extra hot. I would just suggest lifting up the apparatus and removing the heat source from under it. Alright, so now we're going to let it cool, and then we will add 10 mils of water to try to do our first water extraction. I would leave the condenser on for at least for a little while, if not until it gets back to room temperature. But realistically, you could probably take off the condenser once it stops dripping.